Log on, tune in, find out. Another good idea from Cambridge.
Mathematical Sciences, I thought this title was appropriate. It was actually written for a meeting in Boulder where they were expecting to get a lot of mathematicians that didn't, but tries to give the idea that meteorologists do some proper mathematics sometimes. It includes some material from a talk given here by Yoden as a workshop in December 2008, and also some calculations done by two people at the Met Office. So those are the main topics. Now, ever since the early 1900s, people have recognised the behaviour of the atmosphere and the ocean, of course, is governed by the compressible Navier-Stokes equations and the laws of thermodynamics, with additional terms representing source terms and so on. And everyone then, there's been a large tendency among particularly operational people, and operational people includes production climate modelers, let's say, rather than climate researchers, that therefore you didn't have to worry about fluid dynamics anymore. You knew the equations and you just wrote a computer program and solved them. And obviously a lot of dynamical meteorologists have done a lot of work in trying to understand what was going on, and the two strands really got completely separate. So you had operational people think, well, we've just written down the equations of motion, all we have to do is solve them, don't need to worry about dynamical meteorology anymore. And dynamical meteorologists saying you really do need to understand what you're doing. And obviously the same applies to climate, but even more so because some of the equations involved in climate change are much less well posed than these. Now, everyone believes these equations do describe fluids, and if you now got very big computers and you can simulate fairly large laboratory experiments properly with the correct viscosity and diffusivity, and they stand up very well, so everyone believes these equations are correct, and they're also nothing particularly special about solving them numerically. You just use a decent solver and you get a good answer. But in anything like an operational context, the solutions are just far too complicated to compute. And you can tell what the solutions are like by just looking out of the window or looking at a satellite picture. They're just too complicated. There's no way to get anywhere near resolving the solutions. And I was brought up in numerical analysis, and it says you need about 10 grid points per wavelength to get any sort of accuracy. You think of the sort of scales you see outside the window. It's absolutely, you've got a grid length, say 10 kilometres or maybe 50 kilometres. The idea you solve these equations is just absurd, essentially. So the real question is, why on earth do we get any decent answers? Because to solve them accurately, we need computers 30 orders of magnitude faster than we have now, and I don't think even, well, maybe come back in 100 years, maybe that will have been achieved, but there's no way it's going to be achieved while I'm around, let's say. So the real issue is why we do as well as we do, rather than why there are errors. So this is where the dynamical meteorologists come back in, and this talk is really trying to reinforce the links between dynamical understanding and operational practice, which obviously is even more important for climate because you can't verify the answer and you can't afford to get it wrong. So you only get one chance of getting the climate right. So first of all, if you study mathematics with the Navier-Stokes equations directly, you find that what you're doing is focusing on the smallest scales there are. In other words, you're looking at turbulent microscales. You look at the terms which have the most derivatives on them, which are the viscous terms, and you find you're studying the scale of what happens in the atmosphere on a scale of about a couple of millimetres. Now, to understand anything else, you have to approximate the equations to isolate the larger scale behaviour. But larger scale means all sorts of different things, and so you need to derive a sort of portfolio of limit equations to describe the phenomena you're interested in. And the mathematicians come in because you have to write down equations which can actually be solved, and meteorologists are very bad at this. They write down incredibly exotic equations which they say are 100th order accurate approximations to Navier-Stokes in a certain limit. There's absolutely no way it can be solved for more than about a nanosecond. So you need to, as well as write them down, you need to prove they can be solved. And this is where the serious mathematics comes in, and it's where mathematicians can be very useful. You've also got to show the solutions, the asymptotic regime you have defined makes physical sense. In other words, you don't want to make a small scale approximation and a large scale approximation at the same time, and that is another issue with especially mathematicians who say we've got to solve this equation somehow, so we'll just add viscosity. But if you made an approximation that's only valid on a scale of more than 10 kilometres, no way you should be adding viscosity, which is only relevant on a scale of about 1 millimetre. So you've got to keep the physics and the mathematics together all the time, which is obviously quite difficult. So the basic methodology is well established in fluid mechanics and dynamical meteorology. So you choose some small parameters and you're going to expand in the small parameters. But traditional meteorologists tend to forget just how many small parameters there need to be. So we have the Rossby number, which represents how dominant the Earth's rotation is. We have the Froude number, which says how strongly stratified the atmosphere is. That's really the critical thing for small-scale forecasting, with stratification varies a lot. And we've got outside the window at the moment, we're starting to get a very strongly stratified regime where we're going to get cold air near the ground and a lot of possible frost and fog. While the weekend before last we had a very unstable regime with high Froude number and a lot of convective systems and heavy rain. Then we have things which meteorologists don't worry about because they're essentially always small, like the Mach number, but obviously in other application areas that's very important. And the Reynolds number, which you can safely assume is always huge. You have an aspect ratio, which can be various different things according to what you're doing, and the ratio of the horizontal scale to the Earth's radius. That's important if you're looking at very large scale weather and climate. Now, a lot of papers in the literature have said, well, let's just lump everything into one parameter epsilon and say it's some function of all the others, but that only allows you to look at one particular case, and the important thing is to realise you need to look at a lot of different cases if you're going to understand what's going on. So you choose an appropriate limit. Rupert Klein is one of the people who's popularised this a lot, and he talks about distinguished limits. So you require several parameters to tend to zero in a prescribed ratio. And there's no one right way of doing this. You want to, in fact, choose a number of possibilities in order to understand what happens. And the rules of the game are that the smallest parameter has to be taken to zero before the others. So, for instance, the Reynolds number in the atmosphere is huge, so 1 over the Reynolds number has to be taken to zero before you do anything else, for instance. Traditional dynamical meteorology tends to talk purely about small Rossby number and to some extent small Froude number, but now we can do a lot more things. We need to look at a much bigger variety of limits. So I'll illustrate all this with the global shallow water equations, which is not in any sense a real...
Mike, can you give an example where it actually really goes wrong if you take the wrong order of the parameters? So that you have like a bifurcation really in this parameter space that depends on which order you take the limit? Okay, well the best example I think of is when you take if you have the shallow atmosphere approximation and the geostrophic momentum approximation. So the shallow atmosphere approximation is very accurate. Probably the errors are about 0.001. In fact, a lot of people run operational models with the shallow atmosphere approximation. And geostrophic momentum approximation requires horizontal scales of maybe 100 or 1,000 kilometres, so it's much less accurate. If you make the geostrophic momentum approximation first, so here's the Earth, and there's the atmosphere. It's very thin, that's the shallow atmosphere approximation. There's the axis of rotation, so the geostrophic momentum approximation says that the special direction is that. So that says that all the flow will be in round sort of shells like this aligned on the axis of rotation. If you do a laboratory experiment which is very rapidly rotating with a sort of thin shell like that, essentially the flow will all go normal to the axis of rotation. Now that is absolutely nothing like the Earth's atmosphere at all. So that will be a case where if you did it the wrong way around in the Earth's atmosphere, you get something completely wrong. Right, so this is where Yoden showed some extremely nice computations. Not sure if any of the same people are here now that were there then, but well worth. Also, he did a very nice series of systematic experiments. I'll just show you the highlights. It's obviously been published in that paper. And the key thing was the change in behaviour from long-lived coherent vortices, which is the left-hand picture. Light's not showing them terribly well, but I hope you can see that. And
sort of streakiness where all the preferred flow is purely zonal, in other words, parallel to the equator, something like that. And this comes about, essentially took a fixed rotation rate and changed the Froude number, which is the depth of the fluid. So these are sort of two different cases. And so that's, don't worry at the moment about the full list of experiments. I always just used his slides directly. I haven't sort of cut them down to the key points. So the key numbers you have to think about are the Rhines wave number, and that tells you how important the variation of the rotation, effective rotation rate with latitude is. And if the scale is small, if that scale is smaller than the radius of deformation, then that tends to dominate what happens, and that says the preferred flow is parallel to the equator because that doesn't see the effect of the variable rotation rate. The radius of deformation essentially depends on the depth of the fluid, and that says on what scale rotation dominates stratification. So flow is essentially geostrophic, and so the radius of deformation always goes to infinity at the equator and is something sensible at the poles, and the Rhines wave number always goes to 0 at the pole, and so the scale associated with it goes to infinity at the poles because the rotation rate is constant and is something sensible at the equator. So there's always going to be a crossover between these effects, which is this latitude phi. And what you need to do is see the green lines. Can you see those green lines? Okay, right. So you just change the parameters, and that green line says at what latitude the two effects should be equal, and that should be the crossover between this streaky flow like you see here, essentially zonal flow, and the coherent vortices. If you go up here, you've got coherent vortices up here, streaky flow in there, and as you change the parameters, you go to one or the other nearly everywhere. So that's an example of different regimes with different parameters. Now you can understand this by approximating the shallow water equations by limit equations which are valid in the different cases. So for this purpose I'm only going to look at what we call balanced solutions of shallow water equations. In other words, we're saying that the inertia gravity wave frequency is fast compared with the advection frequency, and you can collapse that into one small parameter epsilon, which is a combination of Rossby number and Froude number, which says that this is small if either the Rossby number is small or the Froude number is small, or both. But then you need to break this case up into different bits to understand these phenomena. So for instance, if the Froude number is small but the Rossby number is not particularly small, you have 2D incompressible Euler is at accurate limit, or the Froude number squared. But as soon as you allow the Rossby number to be small as well, it requires order 1 errors. So this is also called the barotropic vorticity equation. So this is actually only a very good small scale approximation to shallow water, but it's got nothing to do, it essentially breaks down if the rotation is significant, and is often misused for large scale atmospheric flow completely incorrectly. Then you go into the quasi-geostrophic approximation, and this is the sort of traditional meteorological scaling invented by Charney of the 1940s. And essentially you assume that the Froude number was equal to the Rossby number and took that limit, and that's been followed a lot, and often it's thought of as the only limit that matters, but it obviously isn't. And this is leading actually to first order, let's say in Froude number, if the Froude number is equal to the Rossby number. But if the Rossby number tends to 0 faster than the Froude number, it has order 1 errors. Now by essentially an accident, if you take the opposite case where the Rossby number is order 1 and the Froude number tends to 0, the error actually reproduces the two barotropic vorticity equation, and you still get converged order Froude number squared, even though perhaps you shouldn't. So this model again is invalid on large scales, and this is essentially the reason in the 1950s people tried to use quasi-geostrophic model as an operational model, because they thought, well, we've only got very small computers, we can't resolve anything small scale, so it's better to use a geostrophic model. So the quasi-geostrophic model had been developed, was reasonably easy to solve, and it was a total failure. In fact, it did worse than the shallow water model, which is only a two-dimensional model. And you think a three-dimensional model ought to be better. It contained the key mechanism that allows depressions and anticyclones to develop, but it was a total failure. and essentially because people didn't realise at the time that it was invalid on large scales. So the next one is the semi-geostrophic model, which is based on a lot of my examples. That's the area I've done most of my work, but that's obviously just one area. And this is accurate if the Rossby number tends to 0 faster than the Froude number, so it's this limit here. And because on this scale the mass field is more important than the velocity field, the error is typically measured in height, not in velocity. Finally, you can write equations which just use this combined small parameter epsilon, and these are the balance models, and you can form hierarchies of these accurate to as many powers of epsilon you like. And there's quite an industry of doing that. Now this is the issue of solvability. You need to be able to, as well as write down the equations, you need to be able to prove that they can be solved, and then the solution of the full shallow water equations is close to that of the limit equation as your original scale analysis says it should. So this is where we need the serious maths. And quite a bit has been done in some cases. So the barotropic, the 2D Euler equation, you can make estimates for this, and quasi-geostrophic equation, a very complete theory exists for primarily the Bourgeois and Beale paper from 1994. As far as I know, that the error estimates aren't as good as they should be for the 2D Euler case, but I don't know if anyone has done any better since. In the case of the semi-geostrophic model, it's harder. Now, if you're used to this area of mathematics, most of the techniques available assume that if you like, the fast solution, which you're excluding, obeys the constant coefficient wave equation, and you can apply various averaging techniques. We've been hearing about them a lot on the other programs on at the Institute this autumn. But they all rely on having constant coefficient wave equations. And in the case of QG or 2D Euler approximations to the shallow water equations, you essentially linearize the depth of the water. You say the water is quite deep, you have a mean depth and a perturbation, and the mean depth supports waves which have obey a constant coefficient wave equation. And the SG case, where you're saying the depth is not particularly large and the flow is dominated by rotation, that doesn't hold, so it's much harder to analyse that case. So what's been done so far, we have got proof they can be solved for large times, and we also know that Jan Brenier has produced an error estimate comparing it with the full equations, but only it's nothing like an optimal estimate based on the scale analysis. And then we get to the balance equations, in a sense which combine all these cases, and the issue there appears to be that there's very strong evidence they can't be solved without additional regularization, which I'll say a bit more about in a moment. So I'll just demonstrate these limits using computations. Now, people in the past, I'll show a bit more evidence in a moment, show that the typical behaviour of, let's say, the tropospheric flow is best matched by, if you're trying to match that with a shallow water model, the best match comes when you use a depth of about 2 kilometres for the shallow water. So I'm going to show computations where I'm fixing the Rossby number, and I'm going to let the depth of the water vary about a meteorologically relevant value. The numerical methods used were as similar as I could make them. So that's the sort of data I've used. And now we're comparing the full shallow water on the left with the semi-geostrophic model, and on the right with the barotropic vorticity equation. So the relevant gravity wave speed is about there. And so you see the error in the semi-geostrophic model increases as the water gets deeper, and gravity wave speed goes up. The error in the barotropic vorticity equation goes in the opposite direction because it's accurate, but it doesn't asymptote to 0, and this is because the depth is not really any diagnostic variable in the barotropic vorticity equation. It's computed diagnostically by solving a Poisson equation, and the real variable that matters is the vorticity. So there's a big problem in getting the depth right on very large scales, but in a sense you could say it doesn't matter. So if you now take the differences, the errors in winds, so now you're doing something more appropriate for the barotropic vorticity equation. Now this does asymptote to 0 at something like the second order rate it should. And semi-geostrophic model, everything is based on the depth and the geostrophic wind, which is obviously a function of the depth. And this is an error in the total velocity, so it's a diagnosed ageostrophic wind as well as a geostrophic wind, and that error is not very well under control, so you see it just stays fairly constant. I just would point out the errors in the semi-geostrophic model are about 10 times less than they are in the barotropic vorticity equation for both parameters. So just sum those up. So theoretically you should actually get, as the Rossby number over Froude number tends to 0, you should start getting quadratic conversions, but the parameter range I've shown, this ratio is more like order 1, so you're only seeing linear convergence. Total winds, no conclusive result. 2D order shows expected convergence in the winds. So that's an illustration of the expected behaviour, and now we go on to the qualitative nature of the solutions, and that links back to the experiment I showed you by Yoden at the beginning. And this is what this is the issue of 2D turbulence. Now we know that very roughly on very large scales, maybe wave numbers down to about 20 in the atmosphere, you get something like a -3 spectrum, then it goes off to -5/3. And a lot of people have thought, well, that means it must obey 2D, the barotropic vorticity equation, because that's classical 2D turbulence. But I said it's not, that equation is not valid on large scales, so it has to be a bit more to it than that. Now, the classical theory of 2D turbulence depends on energy and entropy scaling differently and both being invariants. And the only way that can work is if there is a cascade, if the cascade to be upscale in energy and downscale in entropy. So that's so if we just look now at the shallow water equations, so if the length scale is much less than the radius of deformation, then the potential entropy, which is used for the potential vorticity is essentially equal to the vorticity on these scales. So you get order k squared dependence if we say the energy has an order 1 dependence. Just look at the ratio between them. Because the energy is primarily kinetic energy on these scales. If you take the opposite case, the potential vorticity is really just the depth field, and the energy is dominated by potential energy. So the potential entropy and the energy actually have the same scaling, and the ratio goes to 1. That's there. Now, if you now look at the behaviour of the two limit equations, so 2D Euler is valid for this case, and it reproduces k-squared behaviour, and you get the 2D turbulence you expect. Now in this case, you don't really expect classical 2D turbulence, because this different scaling has disappeared, so you actually get no preferred cascade direction at all. In fact, you haven't really got turbulence, is probably the best way of putting it. So this is a different game. But 2D Euler doesn't know anything about it, so it carries on with its k-squared, and this is why you get an upscale cascade where you don't, in the atmosphere, you don't really see any evidence of the upscale cascade. I mean, you might see a -3 spectrum, but there's no evidence at all of upscale cascades, because you get in fact you get very persistent anomaly patterns, rather like those vortices I showed you in the original experiments. If you go to so 2D Euler gives you the right answer there, where it should, and the wrong answer here. And SG is the other way around. In this case, it gives you the k-squared, but it has a non-linear term as well, which really gets in the way and means it doesn't do the cascade properly. But in this case, it gets it right. So two limit equations have the right behaviour when they should. And if you think back to Yoden's results, this case is where you have the streaky behaviour coming from the barotropic vorticity equation and allowing for the asymmetry caused by the variable rotation rate. In this case, you get coherent vortices and get no cascade. So everything fits. So just now, the practical importance of this for weather and climate is this one, because the blocking climatology is very important for the regional impacts of things like climate change, and certainly very important for extended range forecasting. And the issue is therefore this changeover at the radius of deformation in obviously standard numerical method will simulate, that's all right. The key thing is what determines the effective radius of deformation of the atmosphere. So we know that blocking patterns don't have the vertical structure of the external normal mode, which will give you a equivalent depth of about 8 kilometres rather than the 2 kilometres that seems to fit best. So I'll just show you a little bit what the data looks like first. So that's just a randomly chosen 500 hectopascal height chart from some episode with plenty of large amplitude blocking patterns like this one near the UK, Europe. And that, if you now go up to 100 hectopascals, you see the whole thing really smudges out. So that 500 hectopascal pattern is not an external mode. It doesn't look the same all the way up, but some of it survives as you go up, but only the low wave number part survives. And that says there's really the effective equivalent depth is much less than you think it is, and this is normally believed to be due to stratospheric wave trapping. Here's another picture. The axes have got lost a bit, but the curve is there. So this is processing up-to-date data, projecting it onto vertical modes of the equations and trying to work out the effective equivalent depth from that. So wave number 0 more projects onto the external mode than anything else, but then you have this big peak at about wave modes 4 to 7 and then more peaks lower down. So the external mode is not particularly dominant. And if you take a sort of standard deviation weighted equivalent depth, you find about the 2 kilometres that was found in the studies of the 1950s. So it seems to just verifies that result, but that result was based very much on matching observed behaviour to forecast performance of shallow water models, so they spent quite a lot of time on it, so you can believe it. So that will give you a raised deformation corresponding to about wave number 4 in middle latitudes, so the large scale persistent blocking patterns correspond to the lower wave numbers as you observed, and the higher wave numbers are much more transient, and you don't get the persistent anomalies on the smaller scales. Now, then the question is, why is it like that? And the normal theory is the Chinese Drazing wave trapping of the lower stratosphere, which depends on the mean winds in the stratosphere. So that says, first of all, you have to represent this correctly in models, essentially. I'll come back to that. One of the key issues is vertical resolution, and we've found had this end as climate models, if you push the top up and have an 85 level model instead of a 50 level model, you do very much better with the blocking climatology, because obviously you can't get this effect right without actually resolving the stratosphere properly. So you need to, at the very least, you need enough vertical resolution, and it's been shown by Adam Scaife in particular that 85 level models perform very much better, and it's likely the next round of AMIP experiments will be done with models that go as high as that from different centres, and that actually has a significant impact on regional climate change predictions, so it's just important just to get that bit right. But vertical resolution alone isn't the only thing, and we know from the experience in the 1980s that adding gravity wave drag to models, which clearly has a big impact on the stratospheric zonal wind climatology, had a big effect on blocking climatology, and probably that's why that happened. Right, so that shows why getting the right limiting behaviour matters. So now we get to the why the mathematics matters and what happens. So term balanced models essentially covers all the cases where either Rossby number or Froude number is small. That's that combined epsilon parameter I mentioned a bit earlier. So they cover all those different limits of the shallow water equations I've illustrated. In most cases, such models can be written as a transport of potential vorticity and solution of elliptic equations with the other variables, and this is this PV inversion idea that Brian Hoskins sort of popularised a lot in the mid-1980s and has been incredibly useful. Now, potential vorticity might be the Ertel potential vorticity, which is conserved by the full Euler equations, or it might be an approximation to it with the same accuracy as the system of equations you're using. So the quasi-geostrophic model conserves the quasi-geostrophic potential vorticity, and the error in the difference between that and the true potential vorticity is the same as or the Rossby number difference, which is the same as the accuracy of the equation, so it's all consistent. So that means you have to solve a transport equation where sigma is the potential vorticity and u is the velocity, and one of the mathematical issues is that equation well posed, and that depends how smooth the velocity is. Now there's classical results of Deperna and Leon showed that that equation defines a Lagrangian trajectory, which is what you need if u is L1 local, which means that if you write down a weak form of that equation by integrating over control volume, then it still makes sense. This has more recently been extended by Ambrosio to BV velocity fields as long as they're divergence free, and that allows you to treat more discontinuous representations of the velocity which you get out of a semi-geostrophic model. So just asking this question brings a lot of serious maths in. And then the other thing you've got to do is you've got to do the PV inversion, and that has to generate a divergence-free BV velocity field. People are not used to what a BV velocity field looks like. Let's just show you that one. The basic idea is you're allowed steps in it, but you're not allowed that. So if you look at an output from an anemometer in the atmosphere, it tends to look like this. Obviously it doesn't go to the smallest possible scale, but I mean the instrument can't measure that anyway. But you tend to think of large scale flow as being sort of piecewise smooth. So this thing is BV, and this thing wouldn't be. Well, it might formally be, but if you include viscosity, but effectively it's not. One way of defining turbulence is to say that it's a BV velocity field means you haven't got turbulence, but that would mean that 2D turbulence wasn't turbulence. But the way I tend to think is that turbulent velocity field is one that's not BV. So if we're looking at balanced approximations, we need BV velocity fields. And if you've got all that, then you can prove that sigma is conserved following the motion. It remains bounded by its initial values, and you can solve for large times, which is what you want in order to understand what's going on. Now, in quasi-geostrophic models and the barotropic vorticity equation, the PV inversion problem involves a constant coefficient Poisson equation, and obviously that's a very classical problem, and it effectively smooths the right-hand side and ensures everything works. So that's why a lot of results have been proved in those cases. But unfortunately, neither of those models are valid on large scales. So if you want to study the large-scale behaviour of the atmosphere or the ocean, that doesn't help me very much. That's because the assumptions of nearly constant static stability and Coriolis parameters are not valid, and you get order 1 errors. So you go from QG to SG, essentially you make the same geostrophic approximation, so that stops you, only valid on large scales of course, but now in the case of SG you don't make essentially you don't make no other approximations, so you allow variable static stability and Coriolis parameter. So now you've got something that is valid on large scales, and remember I said at the beginning you've got to have physically consistent models. They've got to have something that's either, you can't make a large scale and a small scale approximation at the same time, and if like the issue with QG is you make the geostrophic approximation, which is large scale, but then you say the static stability is constant or nearly constant, which is a small scale approximation. So you're describing a self-contradictory regime, which means that it tells you lots of very useful things. It's not quantitatively valid for anything, essentially. Now, balance equations also include these generalizations, and they also allow for the case where the flow is not, the rotation is not the important thing and still just as valid at the equator as anywhere else. Now, so in semi-geostrophic or balance models, the PV inversion procedure is non-linear and state dependent. Now, in conditions where the flow satisfies original assumptions, in other words, everything is large scale, then the equation, you can show the equation will still be elliptic and solvable, but you have to, in order to be able to solve the equation for large time, you've got to be able to control these coefficients as you solve it. So this is why mathematically these problems are much harder, because you have to be able to control the coefficients. Now it looks like, well, we've shown that for a slightly simplified applications of semi-geostrophic theory, we can control the coefficients by using a variational formulation of the problem. And the key benefit of using the variational formulation is to be able to say the coefficients behave are essentially BV. Now in the case of the balance equations, there isn't a variational formulation available, and the evidence is we can't control the coefficients. So it looks like something like semi-geostrophic models is about the best you can do once you have variable coefficients. So just briefly illustrate how the semi-geostrophic mathematics works. It'll be fairly sketchy, of course. I'm just looking at shallow water case with variable Coriolis parameters just to keep life fairly simple. So this is the geostrophic momentum equation. So that's U as G is the geostrophic wind. This is pressure gradient in disguise, and that's the Coriolis term. And this is the continuity equation of shallow water. And in this regime, you mustn't approximate the continuity equation because all the terms in that equation are the same size, which is quite unlike quasi-geostrophic theory, where you say this H has an H bar in it, which is much bigger than the perturbation to H. So you define geostrophic coordinates by this formula, and the reason you choose f to the half is to make sure you end up with this being divergence free. That's the little trick, if you like. So now you have the problem that if the Coriolis parameter is variable, your geostrophic space is now, and the original problem I assumed was just being solved on Euclidean R2. I'm not thinking about the surface of the sphere at the moment. Just again, keep life simple. But even with that restriction, this geostrophic space can't be defined as a coordinate on R2 because you find it's just not a valid coordinate. You have to go to a manifold M which has got some curvature to get you out of the problem of the variations of Coriolis parameter. Sigma is now the mass on M, so you have the mass continuity equation on M which looks like that, and this is divergence free on M. That's why I put the f to the half in. Say M can't be the same as physical space. So now in order to solve the problem, you obviously the potential vorticity is just transported. You have to calculate U given sigma, and this is this has to be solved variationally. This is where this is how you control the coefficients essentially. So if I go back to the equation, now let's try and let me just write that on the board. Correctly. Right, it's just so you can compare it with a. Right, now the way you solve SG is you say that the solution at any time is energy minimizer with respect to Lagrangian displacements consistent with equations. So essentially this UG dot is like capital X dot, and obviously U is like little x dot. So if X is the physical coordinate, then U is obviously little x dot. This is this is your velocity in geostrophic space, so that's an x dot and that's little x dot. So if I now say I have a Lagrangian trajectory in geostrophic space, that's phi, and a trajectory in physical space, so my UG dot turns into that term and my U term turns into this term, and this is and that's just the UG term. So I make variations consistent with the equations by defining them like that, and these are all Lagrangian variations. And you require this map from geostrophic space to physical space to minimize the energy subject to a certain mass sigma, which is the potential vorticity corresponding to a certain mass in physical space. So and enforcing that constraint makes sure that you satisfy the continuity equations. So this is why, so essentially writing down this variational principle allows you to control the solution. Now how it then works is that you first of all, let's now write, go back and right. So if we know the mass in geostrophic space, that means we want to map on M, and that's on gamma, which is physical space, or R2 if you like. So you've got to map M to R2, and you've got to conserve mass, so this map S converts this mass sigma on the manifold to a mass H in physical space, which gets to the fluid. This notation just says the map transfers mass in that way, which is why this subject is always called mass transportation. So what we're doing, we're trying to construct the map that way around. Is we say, well, we know where we are in our geostrophic space, so you set this, so you freeze this end, and therefore you need, as you change your map in physical space, you have to change the geostrophic wind according to that formula. And you'll try to minimise, if you like, geostrophic wind squared, so it comes down to a what's called a mass transport problem. And if you just work through the calculus variations in the normal way, you find that the stationary point corresponds to geostrophic balance, like that, which says, and that's essentially why it's done this way, because you can show that geostrophic balance corresponds to making the energy stationary. But it's a variational way of defining geostrophic balance, which allows you to control the solution. Similarly, you can, by doing the same thing the other way around, you can show that the geostrophic wind on the manifold is the rotated gradient of a potential, which means it's divergence free, and you want it to be divergence free to be able to solve it. Now, you then go on to say that you're looking for solutions that are minimizers, not just stationary solutions, and this is why you add some extra physics to the solution procedure, because it says that you're looking for an energy minimizer, and that can be shown by Glenn Schutz quite a long time ago to correspond to the fact that the semi-geostrophic solution is stable to perturbations governed by the Euler equations. So a case where that's not true is, say, if you had a semi-geostrophic solution with a statically unstable atmosphere, which might formally satisfy the equations, but be completely unphysical. In gas dynamics, it's like having expansion shocks. So you can't, not allowed, it's just unphysical. But mathematically, you have to exclude it by assumption, which is, here is the assumption that you're looking for a minimizer. And going through all that, you find that divergence-free velocity field on the manifold, which is what you want to be able to integrate the equation on the manifold. You've also shown the property that this makes it positive definite, giving you a minimizer, says that the velocity is BV. So this is sort of inertial stability condition, if you like, and this being positive definite says dvg by dx can't be massively negative, or dug by dy can't be massively positive, and so you have a one-sided control on the derivatives. And a one-sided control on the derivatives means that, if you like, all you can do is get a sort of sawtooth like this, so you can go a huge derivative there, the derivative the other way can't be very big, so you end up with something like that, and that control is enough to give you a BV property, which allows you to solve the system. And then since you've got all that, you can solve the problem. Now we then talk about higher order models. I think, well, SG is only, well, it's accurate, it's second order accurate in rather special limits, which is certainly enough to be useful, but you think, well, you can write down all these balanced approximations that are much more accurate than that and aren't restricted to rapid rotation, so why don't we just use those? Now it looks like all you can do is add extra regularization, which is like, for instance, spectral truncation. So a few years ago, Yoko, I can't pronounce his second name, if you know him you'll know, I'll just call him Yoko. He proved a result like that by doing the spectral truncation, and therefore estimating the error in such a model is you have to allow for what the error due to spectral truncation is, which means that if you're just looking at the equations, you have no idea what the spectral structure is. So essentially you have to know the answer before you start. So if we say use the quasi-geostrophic theory, that says that Rossby number tends to 0, solution tends to the QG solution that or the Rossby number. So that tells you something about the solution of the true equations. While here, you're effectively going to have to assume what the solution of the full equations looks like in spectral space before you in order to say anything, so you have to assume the answer. So this is a big disadvantage in terms of understanding things. What is likely to happen, this is plausible but obviously a bit speculative, but a truncated balance model should accurately represent the behaviour of a truncated Navier-Stokes model, which is, of course, an operational model is a truncated Navier-Stokes model. So this explains why balance models are incredibly accurate at simulating the behaviour of operational primitive equation models. But of course their errors are both rather large. If we assume the truncation is within the -5/3 spectrum, which obviously covers all scales from about 100 kilometres downwards, and the energy is essentially quadratic, that will give you an error of about k to the -1/3, where k is the truncation wave number. And that says the models are not very accurate, but that is about the rate of improvement of operational forecasts as you increase the resolution, so it looks essentially correct. So this is not a very strong convergence at all. And then the question is, well, how does that relate to, say, what the Rossby number is? Now, this truncation has to come into play if the Rossby number is order 1 anywhere in the solution, and therefore you really have to apply it at a scale which stops the Rossby number reaching 1. If you don't know any better, you might say, well, the truncation wave number k should be proportional to 1 over the Rossby number, and that will give you the accuracy of the model about Rossby number to the 1/3. The QG result shows you get all the Rossby number with a much cruder approximate model, and that's really telling you that this assumption is far too pessimistic. But the problem is you don't actually know, except from quasi-geostrophic theory or semi-geostrophic theory, what the assumption should be, because this is the problem of having to essentially assume the answer and then make an assumption like this. You really have no idea what to put in instead of that, but in fact that's very pessimistic. So balanced models are much less useful in terms of understanding what's going on because you can't solve them. So that's why mathematics is very important. Right, last topic. So one of the interesting things about the semi-geostrophic model is it has singular solutions, and the question is, are there really valid limits of the Euler equations or not? So this is some computational tests that strongly suggest they are. So this is the other aspect of the whole thing, is do you believe your simple model really is giving you the right limits? So this problem is set up using a vertical cross section, periodic boundary conditions in X, and I haven't bothered to write down the full equations. So you start with fully compressible equations, and you neglect the acceleration terms in the cross section du by dt and dw by dt to define the semi-geostrophic limits of them. In this case, we know the semi-geostrophic system can be solved. That's been proved. Scale analysis suggests it should be second order accurate because of the two-dimensional constraints. So can we verify this? But we also know the semi-geostrophic equations have singular solutions. So that is the semi-geostrophic limit equations, which are written in terms of the sort of geostrophic coordinate b plus fx and z is potential temperature. Summarise. Yeah. Now the best rigorous result that Euler converges to semi-geostrophic is rate of Rossby number to the half, which is way short of the what it should be, which is Rossby number squared. So there's a large gap between what's being proved and what we think happens. Why it's important to do numerical experiments as well, but there's plenty of opportunities for more mathematics there. The other thing I should mention is that this theory of the semi-geostrophic equations only proves the existence of the Lagrangian form of the equation, not Eulerian form of the equations, and that suggests that if you want to get this limiting behaviour right in the Euler equations, you need to use a Lagrangian discretisation of the equations and maybe Lagrangian averaging. And obviously I know there are lots of people here who like that, sort of like Sebastian and Jason, who like those sort of methods. So it's a really good incentive is, can you show that these sort of numerical methods can get this limit right and others can't, because then there's a good case for using them in a real system. So that just summarises the computational test, which is fairly standard. So it's very difficult to solve the semi-geostrophic equations directly in this case, except not by conventional numerical methods. So what I'm doing is simply using the unified model, which is fully compressible Euler, and I'm letting the Rossby number tend to 0 by using a scaling of variables that says that the limit solution, the semi-geostrophic solution, is invariant to the Rossby number. So essentially I'm aiming at a fixed target, and what I have to do is to show that, as well as the solutions getting closer together as Rossby number tends to 0, that the limit solution of the UM satisfies the semi-geostrophic equations, and I do that by checking this unbalanced ratio. I need to show that converges to 0, because in the limit, if that is 0, then the solution is actually a semi-geostrophic solution. So UM uses semi-Lagrangian advection, which is consistent with Lagrangian solutions. Might be able to even do better at. So two things I've looked at: convergence in of the wind along the front, and that's into the cross section, and the potential temperature. So the two lower times are before the discontinuity forms, and what I'm showing there is the expected second order rate of convergence. Now here what I'm converging to, measuring the difference from, is the unified model solution at the smallest Rossby number I've run with, which is 0.03, and so if you like, the truth was calculated there, and I'm looking at the differences from that, and you're seeing the bottom two lines are showing second order convergence. The left hand picture is when the semi-Lagrangian advection was just on standard operational scheme, and this is where you enforce monotonicity or quasi-monotonicity on the interpolation. These two curves are after the front form. You're still seeing convergence, but the rate is not quite as good. But the values of the differences are somewhat lower when you use quasi-monotone advection, suggesting that's helping the process, but it's not essential. So here's potential temperature, and essentially the same message. So the bottom two curves, solution is smooth, you get second order convergence like you should. Here you still get convergence, but sort of more like first order or a bit better, and the difference is smaller with quasi-monotone advection. And then this is the test: are you actually converging to SG? Because I haven't actually got a solution of SG on the board, but say if this tends to 0, if the balance tends to 0, that is a solution of SG in that case, and we see the same message. We are clearly converging to SG, second order rate when it's smooth, something like first order rate when it's not, and significantly smaller differences when you have quasi-monotone advection. So comments reflect what I've just said, I think. So that shows, if you like, indirectly that the limit does satisfy the semi-geostrophic equations. Now the reason I haven't got a numerical solution of the semi-geostrophic equations on the board is that in those equations the trajectory in the cross section U and W are computed implicitly, and you really need to use semi-Lagrangian advection, which means, and you have to find an implicit calculation of the departure points in the semi-Lagrangian scheme in order to be able to do that. And we don't have a satisfactory way of doing that. That's one of the issues, if you like, was trying to compute semi-geostrophic solutions, and therefore in order to make it you have to use Eulerian advection, and then you have to do a lot of smoothing at the front, which means the solutions are not very good at all. So I haven't shown you those. So it's better, so in a sense what's happening is by solving the unified model, which is fully compressible, you can actually possibly reach a semi-geostrophic limit solution more effectively than by trying to solve the limit equations directly, but you need the understanding of what the limit is like and the fact that it's well posed and makes sense in order to be sure that you know what you're doing. So, so that suggests a properly designed scheme for the Euler equations should be able to find this limit. And that's what you want, because you don't want to specialise your operational model to one case. You want to be able to solve lots of different limits. So you need to this is a critical test. So that shows we get approximately first order convergence rate for the discontinuous case, suggests the discontinuous limit is correct and should be respected in operational models. Obviously in the real system we see lots of fronts all over the place, so physically you believe it's correct, and mathematically it seems a bit contentious.
Mike, coming back to the simulations of the unified model, I seem to remember that you said, or you had some results at some point where you said that the unified model wasn't able to reproduce several cycles of
That's right, so I've only shown you one cycle.
Right.
And so it's still an open question whether you can simulate the multiple life cycle. I haven't seen any successful simulations of that yet.
Right.
So that's the key challenge now. Now I couldn't do that with the unified model is fully compressible. Now if you write a cross-section version of the unified fully compressible equation, that equation in the cross-section are not a valid solution of the three-dimensional equations because of the nonlinear equation of state. So you realised you couldn't do the test with this. And what happens is you form the front, it equilibrates, and then everything just gets stuck and nothing happens. And I'm pretty sure that solution is correct, and Colin Cotter has had a hard look at that as well. He agrees with that. In fact, he's the one who pointed it out first. So it looks like to do the multiple life cycles, you have to use the Boussinesq system rather than the fully compressible system, because then the 2D model is a valid subset of the 3D model. So that is the challenge now. If you want, can you show particle methods or and the sort of things you're doing, can you show you can get the multiple life cycle? But you have to do it in the incompressible case, unfortunately. So the test to the level that just produced the initial front is passed, but that's not the interesting one in a sense. So I've done the things I've said there. Hopefully shown you that mathematics is useful in improving operational models and understanding what the atmosphere is like. Okay.
Thank you.
Not quite sure I understood correctly. You showed at the beginning, when you showed the convergence, you showed that you didn't get the right convergence of SG with respect to shallow water.
That was when I was looking at this one of the early slides when I was looking at convergence. Right, you get the right rate if you look at convergence rate is all the prognostic variables are really all the H field because it's like the geostrophic wind is just the grade of H.
Yes.
So you haven't got if you include the A geostrophic wind, you should get second order convergence, but I wasn't looking at a small enough parameter to see that.
Yeah, I wonder whether that is the reason. I mean, the way you compare is, I mean, you basically do some asymptotics and then you've got two equations and you just compare the equation, the solutions. The way Marcel Oliver would look at the problem is that you derive QG in terms of a transformation.
Yeah.
So what you really want to do is, in his view, is you don't just compare the fields. You actually have to take into account the transformation, and maybe that will give you the right convergence rate. We've done this. We're doing this at the moment, or trying to do something similar with David Richard together.
Maybe I should process the answer to that computation differently. Is that your message?
No. The message is that you can't just barely compare the fields. You can't just say the H field in QG is equal to the H field.
Yeah.
They're just in different coordinates.
Yeah.
So you have to use if you really want to compare, you have to use the transformation. You have to go from one level up or down. And it seems that the convergence rate, we don't have final results there, but it seems that it's quite sensitive towards this transformation. So maybe that could...
I think in this, what happens with the error in the total velocity in the semi-geostrophic model, so if your Rossby number really is small, it should be second order, but as the Rossby number goes up to order 1, you can actually get the B of E control only applies to geostrophic winds. You have very good control of the geostrophic wind, however big the Rossby number is. But the ageostrophic wind can blow up. You can get, so essentially you measure value solutions. So if you have the Rossby number going up to order 1, the error in the ageostrophic wind is getting very out of control. And a good example of that is if you think of in the vertical direction, if you have strong static stability, the vertical motion produced by the omega equation is fairly small. So, and that's sort of thing that should be well predicted by a balance model. If you make the static stability weaker and weaker, the vertical motion gets bigger and bigger. You have a sort of inversely proportional static stability. So if you have very weak static stability, you're going to get huge vertical motions. So the error is really completely out of control. And I think you'll sort of see, I think in this particular case, you're seeing that effect rather than the effect you're talking about. That problem, that sort of reason makes it, that applies to nonlinear balance models as well, actually is quite a serious problem in using balance as a diagnostic tool in operational systems because of this blow up as the control gets weaker. Oops.
Good day, Mike.